All right, everybody. Today's lesson is going to be on weak acids. And I think I'll probably have to split this up into multiple videos. It's kind of a longer lesson. But here's the first one. First, let's review in our definition early on of an acid and a base. We use the Bronsted-Lowry definition, which basically said that acids are proton donors. What that really means is acids are the ones that lose the H+, or for our purposes, we just look for an H. Don't worry about the charge so much. So acids are the ones that lose the H, and bases are the ones that gain or accept the H. So if you look at this first example, and you should know this one already because you were supposed to start memorizing the CH3COOH as a particular thing. But let's see if it's an acid or a base. So what does it become? Looking at this reactant compared to the products, this looks pretty similar. It must have become this. What is that? How are they different? CH3COO minus. What's missing from the original molecule? There's a hydrogen missing, specifically an H plus. So if the hydrogen is missing, that means the original reactant here, CH3COOH, donated or lost the H plus, making it by definition the acid. Similarly, the other reactant, therefore, in an acid-base reaction, if we know that CH3COOH, acetic acid, is the acid, then the other reactant has to be the base. But let's just check to make sure. H2O is water. What does it become? H3O plus. What happened to it? It gained a hydrogen. So by definition, H2O gains a hydrogen. It must be the base, and it is. So it makes sense. All right, so that's how we define acids and bases. We just look at what they become, whether they gained or lost the hydrogen, H+. The last unit we talked about electrolytes, or the last lesson we talked about electrolytes, strong versus weak electrolytes. We said strong electrolytes really conduct electricity very well because they've got lots of ions, versus weak electrolytes only conduct electricity a little bit because they don't have as many ions. So let's turn on into a definition for strong acids and versus weak acids. Same thing with bases, though. So strong acid fully dissociates into ionized. In other words, it 100% ionizes. So hydrochloric acid is our classic strong acid. When you put that in water, you will not find an HCl molecule anymore. All you will find are H plus ions and Cl minus ions. The H plus ions actually hook a ride onto a water molecule. So you would actually see those as H3O pluses, but never mind that. It's okay to write it as just H plus and the chloride ions. So it's all ions, which means, hey, that should support electricity really well. And that's why they're good conductors of electricity, because there's lots of ions. And that's true for bases as well. That's an example of an acid, but it's also true for a strong base. Lots of ions because it 100% ionizes. All right. In contrast, we have these weak acids and weak bases, which are going to be weak electrolytes because there's not as many ions. And that's kind of gets to the heart of what a weak acid or a weak base is. It doesn't produce as many ions. And we need to figure out why not a little bit, or at least discuss it a little bit. Here's an example, again, of our acetic acid. It is a weak acid, though. So when acetic acid molecules are mixed with water, some of those molecules break into H plus ions, and these are acetate ions. Some. If you see right there, it's temperature dependent. But if you look at the temperature at 25 degrees Celsius, pretty close to normal room temperature, it's a very small amount that's actually the ions, about 0.4%. Less than 1% is ions, meaning over 99% still are these molecules. Those molecules don't affect the pH. pH is all about H plus ion concentration. So since 99+% of your solution is still molecules, you're not going to have a big change to your pH with a weak acid like acetic acid. And that's also because we don't have a lot of ions. It's also why we said it's a weak electrolyte. It's not as good a conductor of electricity. Take a look at this particle diagram I quickly drew on the board. You can admire my drawing skills later. But here they are. There's HI solution and HF. You can tell which one is which and which one is a strong versus weak. But let's just look at the picture, the the particle diagram and see if it all makes sense and if we can guess which is which. One of them is going to be strong, one of them is going to be weak. Here's the HI solution, and they don't even give you a key for what the HI molecule would look like. And let's just pretend it looks like a big green and a little blue. Okay, can you find any big green and little blue molecules floating around in that solution? You cannot, because there aren't any. Instead, all we have is the I- ions. There's a whole bunch of them. And we have a whole bunch of these H3O plus. They put it the proper way. Instead of H plus ions, they put it the H plus attached to a water molecule. That's actually most correct. So someone was being really correct here. Anyway, so because it's all ions, 100% ions, no more molecules, we can be like, hey, that's a strong acid. HI is a strong acid. Compare that to HF solution over here. They give you in the key what the HF molecule looks like. It's a little blue and big green together, which I see a lot of. In fact, most of these are HF molecules. There's only one that I see that's just an F minus by itself and an H3O plus by itself. So basically, one set broke into ions. The rest of them stayed as molecules, which would be pretty obvious to say that the HF is a weak acid because it only partly ionized. Hopefully that makes sense. So let's talk about why. What made the HI solution fully ionized compared to the HF solution only partly ionized? Some of that full explanation is not really for our course. It's for a more advanced chemistry course. But at least let's talk about what is happening. What's happening is to get partial ionization. It's not like someone's in there and be like, okay, you break into ions, you stay together. Any of the molecules have the ability to break into ions at any given point. The issue here is that this is a reversible reaction. And we've talked about different types of equilibrium so far. We haven't talked about chemical equilibrium yet, so this is going to be our first taste of it. But here's the deal, and this is actually more common than you would expect, I think. When we talk about a reaction, let's look at this one right here. NH3 reacting with water. This is an acid-base reaction. NH3 you're supposed to memorize already, so you should already know what this one is. But just take a look. NH3 is becoming NH4 plus. Ooh, there's 4 hydrogens now, where there were 3. It must have gained or accepted a hydrogen, making NH3 by definition the base, and water must be the acid, and you can check that out. Look, it has 2 hydrogens originally. Now it only has 1. So yeah, it gave up a hydrogen. So that's an acid. So it's an acid-base reaction, right? So NH3 molecules react with water molecules. They turn into these 2 ions. Once you have these ions, it turns out the ions can react with each other, hydroxide and NH4. They can react to form the original molecules. It's like undoing what you just did, but it happens. So you have reactions that can go both ways. That's a reversible reaction. We show that by a double-sided arrow, like right there. And you could stack them, the 2 arrows on top of each other, or put them side by side like I have them here. Either way is fine. But the point is, a lot of reactions are reversible, believe it or not. And it's definitely going to be true on any weak acid or weak base. They're reversible reactions. At some point, when you have 2 reactions kind of, trying to counteract each other, they're going to reach a point where the rate of both reactions are equal. That's where we talk about equilibrium. And we already looked at this different types of equilibrium, right? When we had a bottle of water in a closed container, like what is hopefully still sitting up above my cabinets there for the year. The closed container should have the same amount of water the whole year. It looks like nothing's happening, right? And we were supposed to learn that no, evaporation of that water will continue. Even though it doesn't look like it's continuing, it's still continuing. It's just that an equal amount of condensation is counteracting the evaporation that continues. So they balance each other out. There's equal rates of condensation, equal rate of evaporation. Same thing is true when we're at equilibrium with this reaction. The rate that the ions form molecules are going to balance out the rate that the molecules form ions. So that's not necessarily halfway. We'll talk about that next unit. It's not halfway. It's not like you're going to have equal amounts of each. It's some point, and you're going to have a nice steady concentration of everything. So it looks like nothing's happening, but Again, we were supposed to learn that there is stuff happening. There will be some math involved in this, but we'll say that for the end. For now, though, let's talk about conjugate pairs. You read about this in the guided reading. Hopefully it made sense. But you have conjugate pairs, and conjugate pairs, just by definition, they're basically the same molecule, just one of the pairs is missing a hydrogen, the other pair has gained the hydrogen. So let's see if we can identify some conjugate pairs. I'm going to switch to this right here. All right, so NH3, you're supposed to memorize that as a base. It's a weak base. Where is its conjugate pair? Its conjugate pair should be pretty much the same exact thing, except either one less hydrogen or one more hydrogen. Ooh, this looks pretty similar. Those must be conjugate pairs. They are. NH3 had 3 hydrogens, NH4 plus has 4. So the only difference is the NH4 plus has 1 more H plus. But that makes them conjugate pairs. One of the conjugate pair will always be an acid. The other one of the pair will be a base. It's already labeled right here, but you could take a look at the reaction. NH3 in this reaction, the forward reaction, is gaining a hydrogen. So by definition, making it a base. So NH3 is our original base. Its conjugate pair, we can now label as an acid. Why? Because a conjugate pair will always be one of them's acid, one of them's base. But also, if you look at the reverse reaction, check it out. NH4 plus reacting with hydroxide ions. What happens? What do they turn into? We're trying to look this way, look backwards here. It's going this direction. NH4 plus turns into NH3. It did that by donating or losing a hydrogen, which by definition makes it an acid in the reverse direction. Similarly, we can look at the other conjugate pair. Let's use a different color. How about yellow? H2O in this reaction is acting like an acid because it's losing the hydrogen. Its conjugate pair, that's a nice circle-y line. Oh boy, what happened? Oops. Its conjugate pair is this hydroxide ion. H2O and OH minus are conjugate pairs. The H2O is the original acid. Its conjugate pair over here, the hydroxide, must be the conjugate. We call it a conjugate base, but they're conjugate pairs. So sometimes you're asked, can you identify a conjugate pair in this reaction? Yeah, you just pick the two that are pretty darn similar to each other. That's your conjugate pair. But usually you'll have to say, all right, pick a conjugate pair and identify which is the acid, which is the base. So let's try that right here. And you can choose either one usually, or sometimes you're starting with one thing and you're like, okay, what's the conjugate to this molecule? So let's try both questions. First, let's just identify a conjugate pair and say which one's the acid and which one's the base. So I'm going to choose the big one right here. Let's choose this guy. What's its conjugate pair? Oh, this thing that looks pretty similar to it? Yeah, that's a conjugate pair. Which one's the acid? Which one's the base? If you look at the forward reaction, never mind that this is actually called an acid, but CH3COOH looks like it gives up or donates the H plus. So by definition, this must be an acid. Boom. So here's one conjugate pair. CH3COOH is the acid. CH3COO minus is the base in that conjugate pair. Ta-da! Great. But another question might be, all right, check out, let's use a different color. Check out water in this reaction. That's a great circle I drew. Check out water. What is its conjugate? Not even identify acid or base. What is the conjugate pair to water? Well, you wouldn't want to choose the acetate ion because, first of all, they don't look anything similar. How could they be conjugate pairs? They have to only be different by a hydrogen. They're different by like some carbons and an oxygen and a hydrogen. So no way is that a good choice. You also wouldn't choose the other reactant. Again, they're only supposed to be different. Conjugate pairs are only supposed to be different by a hydrogen. How could they be conjugate pairs? That's crazy. The actual answer would be this guy right here. Because how are they different? They're different by hydrogen. This one has 2 hydrogen. This one has the 3 hydrogens. Specifically H plus, of course, I should mention. Okay, so that's how you can identify different kind of, or you can answer some kind of questions about conjugate pairs. Hopefully that makes sense. I'm going to pause it and we're going to do a different video for the last part of Ka. You could do the front side of those questions on weak acid questions.